Hello, here is the question number 27, which reads, a circuit consists of two inductances L1 and L2, a resistance R, a two-way switch, a battery of electromotive force E and internal resistance R. The switch was in position 2 for a long time, and at t equal to 0, it is thrown to the position 3. So from 1 it was connected to 2, now you are going to connect it with 1 with this 3. We need to find the current through the switch as a function of time after the switching, and we need to find total heat dissipated in the resistance after the switching. So just before t0, t equal to 0, that means since long time it was connected to with this 2. So what would have been the current running through these elements we can think of? So just before t equal to 0, the circuit would be like this. That means there's a battery, then internal resistance I have shown, and these inductors will be like just wires, so they will not oppose any current, so current will be flowing like this, and there will be no current flowing through this resistance. So we can use this circuit to find out the I0 value. I0 is going to be E by R, so that will be the current flowing through these two inductors. Now we know when the switch is suddenly changed, then there is no change in the flux on these inductors, and this current is I0, so we can link the current to. Now after t equal to 0, the circuit would be like this, because this battery is now no more connected. So circuit will have two inductors and resistance only, so I have not shown this battery, and here this inductor L1, L2 is going to be their resistances are. Now we know since we have changed this switch from 2 to 3, then just after the switching you'll find this will have a current I0, this will have a current I0, current will not suddenly change. However, the inductor L1 will have zero potential difference across it. Since it has zero potential difference across it, that means it will maintain its flux. Why? Because the EMF is going to be 0, that's it, d phi by dt will be 0, that means flux will not change. Since L1 it does not change its value, so it will also not change its current. That means this L1 will maintain this I0 current for all the times, and that I0 current will move around the circuit. Now what happens to this L2? L2 will start with I0 current, but this current will go through this resistor, so this resistor will decrease the current over the time. So the current through this L2 is going to decrease. So I have considered the current through L2 as I, then I comes here and passes through this resistor. And this inductor maintains I0. So this current and this current, here the current will become I plus I0. And this I plus I0 goes up to here. So this I comes over up to this point, and here the current maintains I0. So this current should not change. So this current remains I0. Now we want this current to I0. This current is coming as I. So what should be the current coming from this through this switch? So that can be found out by using the junction law. So we will say if this current and this current is here, so this current must be, since this is incoming current, so we will write total outgoing current minus this, that means it's going to be like I0 minus I. Now this current must be I0 minus I, or we can have this junction law over here. I0 is coming, I is going, so the remaining current must be running over here, which is I0 minus I. So since this conductor is perfect, so it will have any amount of current which is needed. So here you will find I0 minus I current will be going. And the question asks what is the current flowing through the switch, so this is the current we are requiring. Now what this I current is going to be, now look at this I current. This I current is following a circuit which is a inductor and a resistance, and this is basically going like this. So that is going to be Lrdk circuit. In Lrdk circuit, current goes like I is equal to I0 e raised to power minus RT by L, which L it is using L2, so that is going to be the current at an instant of time. And I0 remains constant, so the current through the switch remains I0 minus I. I0 is I0, I is this number, so we can substitute over here, catch this I0 outside, so it will be like 1 minus e raised to power RT by L2. So this current in through the switch is going to be I0, which is E by R, so we can write like E by R within bracket 1 minus e raised to power RT by L2. That's our final response for first part. Now we need to solve the second part, total heat dissipated through the resistances. We got this current as a function of time, so we can find the heat amount from this, or we can use the stored energy stuff because there's no battery connected. So total heat dissipated in R is going to be H is equal to I square R dt running from 0 to infinity. Or we can say this is also equal to the loss in energy of L2. Why L2 only? Because L1 maintains its energy. So just after switching the circuit, this had I naught current, and this I naught current will keep on flowing forever. However, the current I, which goes from I naught value to 0, this will decay over time. So this will lose its stored energy, and whatever the energy it is losing, that must be wasted as a heat by the resistance. So loss of in energy of L2, which is initially it was half L2 I naught square, finally current will become 0, then you'll find 0. So the heat dissipated can be written as L2, I naught is E by R, so we can substitute over here, so it's become E square divided by 2R square. So that's the expression for total heat dissipated in resistance after switch was shifted. And this is the expression of the current passing through this switch after it was shifted at any time t. So these are the two responses for part A and part B. Thank you.